Okay, kids, I'm going to see if I can get through this video pretty quickly, but we're talking about logistic growth equations, and it's the type of growth that really makes sense in the world, that there usually is not unbridled or uncontrollable growth that just keeps going and going. There's usually something such as a carrying capacity that limits the amount of growth that we have. So in exponential growth, we assume the rate of increase or decrease of a population at any time is directly proportional to the population. In other words, we have this little equation, right? However, in many situations, population levels or growth levels off and approaches a limiting number, L, the carrying capacity, because of limited resources. In this situation, the rate of increase or decrease is directly proportional to both P and L minus P. This type of growth is called logistics growth. It is modeled by the differential equation dP over dt is equal to Kp times the quantity L minus P. If we then look at the second derivative, we can find out an important fact about the time when P is growing fastest, because the second derivative provides information about the point of inflection, if you will. So let's start off with this first one, though. We have the population P of T of fish in a lake satisfies the logistic differential equation dP dt is equal to 3P minus P squared over 6,000, where T is measured in years and P of 0 is equal to 4,000. P of 0, we have our initial time then. So with this, we're going to do a little bit of rewriting here. So we would have dP dt, let's rewrite this, dP dt is equal to, I'm going to do a little bit of weird factoring. I'm going to factor out a 6,000 from the denominator, 1 over 6,000, because I really want to see what is left in this grouping. Now, if you notice, I still have the P, and when I factor 1 over 6,000, I get 18,000 minus P. Oops, if I factor that out, okay? So I factored a P out from both terms and a 1 over 6,000, right? So the limit as T goes to infinity here of P of T then is then going to be 18,000. Okay, so the function P of T, the highest that it can get is 18,000. Okay, what is the range of the solution for the curve? Then the range of the solution, P of 0 is 4,000, so it's going to have a low of 4,000. And then P is going to then have a high of 18,000. And I said this is theoretical, but, in practicality, sometimes population can grow a little bit bigger and then it gets pulled back down due to the carrying capacity of the environment. So for what values of P is the solution curve increasing, decreasing, justify your answer? So what we're going to do is we're going to take dP dt and we're going to set it equal to 0. So we have 1 over 6,000. Times P times 18,000 minus P, and that's equal to 0. So we could say that occurs when, I'm going to draw a little arrow here, when P is equal to 0 or 18,000. Limit my space here, 18,000. Okay, so that's where our derivative is equal to 0. So we're going to make a little table here. Sometimes we can make a table since I can do a number line, but tables are just as useful. So if I talk about P and dP dt, then we know that at 0, we know the growth rate is 0. Then at 9,000, I'm going to use that as a test mark. And then I have at 18,000, that's where we know the derivative is equal to 0. And then I'm going to use a test point after 18,000, even though I know what's going to happen, we're saying that we can't use values for that, but the equation is going to pull the value back down. So it is kind of important that you note this. So if I plug in 9,000, then it turns out that dP dt is positive, and then if I plug in 20,000, dP dt is negative. Now, it's kind of interesting to see what will happen here if we do have a real situation like this, that it would go from 0 to 18,000, and then that would be increasing. And then from 18,000 to to infinity, it would then be decreasing if, in fact, the values did go above that. But as I said, in the critical numbers here, from 0 to 18,000, then the function will be increasing. Interesting about the endpoints here, just hang on to that for just a second. Okay. Then for what values of P is the solution curve concave up? So we're going to take dp/dt, and given that it's 3p minus p squared over 6,000, and then I'm going to take the derivative of that, so the second derivative with respect to time twice, then is equal to 3 dp/dt. Remember, p is the dependent variable, so we have to use the chain rule with that, minus then we get 2p, 2p dp/dt, and I'm just going to carry the 6,000 with me there, and I'll do some simplifying now. So we get the second derivative, dp/dt, is then equal to dp/dt, the second derivative, dp/dt, and then times, and I'm going to do a little factoring here, 3 minus, and then p over 3,000. Simplifying that expression. So take a minute, pause the video if you have to, and check to see how I got that. Factoring out the dp/dt. And then I'm going to plug in, I'm going to pull out, pull out, I've got d2p over dt, the second derivative, is then equal, I'm going to take this, and much like I did initially when I pulled out the 1 over 6,000, I'm going to pull out 1 over 3,000 here. And then I still have the dp/dt here. And when I do that, I get 9,000 minus p. So it allows you to see that limiting characteristic there. So with this, then now I have 3 factors, right? So I want to know when is I want to know where is the graph concave up or concave down. So if we look at the second derivative, I can say, where is it equal to 0? Clearly it's not undefined there. And that occurs when p is equal to 9,000. Or for when the derivative is equal to 0. So that's when dp/dt is equal to 0. I don't want to run out of room here. But when dp/dt is equal to 0, and that occurs when p is equal to 0 or 18,000. Okay? All right, so then if I look at the p and the t, let's look at a table of values. Surprisingly doing pretty well with the space that I have. So if I start off at 0, we know the second derivative, we have the second derivative there, right? When p is equal to 0, that's when dp/dt is equal to 0. So the second derivative will also be 0. So then I'm going to have to pick a value in between 0 and then the next critical number, which is 9, or not critical number, a possible point of inflection. So I'm going to pick 5,000, and then I've got my 9,000, and then I've got to pick a number between 9,000 and 18,000. So I'm going to pick 12,000, and then 18,000, and then a number after 18,000, 20,000. And so when I use 5,000, plugging that into this equation, then I get a positive second derivative. If I plug in 9,000, I'm going to get 0. If I plug in 12,000, I'm going to get a negative value because I have 9,000. 9,000 minus 12,000 is negative. If I plug in 18,000, and I'm kind of skipping over the dp/dt here. You have the sign for dp/dt. From 9,000 all the way up to 18,000, the sign for dp/dt is going to be positive. So when I put in 12,000, 9,000 minus 12,000 is going to be a negative, so a positive times a negative. And then with 18,000, that's where it's 0. And if I plug in 20,000, I'm going to have a negative times a negative, so that's going to be a positive second derivative, right? So if you look at it, it's going to be concave up then. I'm going to use CU. Concave up and concave down. So it looks like from 0 to 9,000. And then from 18,000 to infinity, then that would be concave up. And kind of sliding along the upper part, if it does go up, then it would be concave up at that point. Concave down, then it would be from 9,000 to 8,000. So does the solution curve have an inflection point? Yes, it does, at P is equal to 9,000, because the second derivative changes sign. And then use the information. So we have our answers all over the place here. I didn't box them up, but hopefully you're able to distinguish what we're looking for here. All right, and then the last question, use information you found to sketch the graph of P of t. So then keep in mind that we are dealing with realistic situations here. So my function then, if it starts down here, see, it all depends on where you're going to start here. We have P of 0 is equal to, P of 0 is equal to 4,000, so it starts down a little bit lower. So we can put a 9,000 in here. And then we can have an upper limit of 18. I'm just going to put that here, 18,000. And so when our graph comes up, we can see that the point of inflection occurs at 9,000. But we can see the graph is concave up from 0 to 9,000, right? So 0 to 9,000, something like that. Once it gets to 9,000, then it's going to go like this, and it's going to level out. Now, interesting, because it's generally going to stay below, but if it does go above, then it would look something like this. And you can kind of see if there is some reason where it starts out above, it's going to, and you'll see that in one of the examples. So I'm going to hold off on that, but it's going to level off to 18,000 and pretty much stay there. But let me stop this video, and then I'm going to go on to the second problem on logistics growth equations. And I will be right back.